Welcome to ElectrAspirant, an assistance to electrical students for objective type exam preparation. It's an initiative of Department of Electrical and Electronics Engineering, Christ College of Engineering, Irnyalakuda. In this video, I would like to discuss some objective problems in control system subject under the topic state space analysis. These are some prerequisites we need to discuss the problems under the state space analysis. Coming to the state space analysis, the state space representation of LTI continuous time system. We have two equations, state equation and output equation. And the state equation is given by x dot t equal to ax of t plus bu of t, and output equation is y of t equal to cx of t plus du of t. So that is the standard representation of state space model of LTI continuous time system. And we have all the terms are illustrated here. Capital A is a state or system matrix, is a square matrix of the order n by n. B, the control matrix of the order n by m, where m is the number of inputs. And C, it is the output matrix of the order p by n, where p is the number of outputs. And capital D, it is direct matrix given. Now the characteristic equation. If you know the system matrix capital A, then we can form the characteristic equation by using determinant Si minus A equal to 0. Also, if we have the state space model, then the transfer function matrix G of S can be obtained by using the formula C Si minus A inverse B plus D. Also, the state transition matrix phi of t is given by inverse Laplace transform of Si minus A inverse or e raised to at. Now the solution of state equation, it is x of t equal to phi of t into x of 0 plus L inverse Si minus A inverse B into U of S. Now in order to check the controllability, we can form the controllability matrix QC as B, AB, A square B, etc. up to A raised to n minus 1B, where small n represents the order of the system. Also, in order to check the observability, we need to form a observability matrix QO, which is defined as C transpose, A transpose, C transpose, A transpose square, C transpose, etc. up to A transpose raised to n minus 1 into C transpose. These are the some equations necessary for discussing state space analysis. Now coming to the first problem, the state variable formulation of a system is given. We have the state space model is there with the initial conditions and the output equation. Now we need to, the options are related to controllability and observability. So in order to solve this problem, we need to form the controllability matrix and observability matrix. Thereby we will get the controllability matrix BAB. It is 1 minus 2, 1 minus 1. And if you are finding the determinant of QC, it is non-zero, which means that the system is completely controllable. And the observability matrix we will form as QO equal to C transpose, A transpose, C transpose. We are getting the matrix as 1 minus 2, 0, 0, such that the determinant QO is equal to 0, which indicates that this given system is not observable. Hence, the answer is A. Now coming to the next question. For the previous problem, find the response y of t to a unit step input. Again, we can do this problem by means of different ways. Here it is illustrated by means of, by observing the given state space representation, it is very clear that it is given in diagonal canonical form, such that we can form the transfer function directly. That is y of s by u of s equal to, you will get by following the diagonal canonical form, we will get the transfer function as 1 by s plus 2 plus 0 by s plus 1, or in other words, the transfer function is 1 by s plus 2. Now to get the response means y of t. To get that, we have y of s equal to u of s into g of s. Then by substituting, we will get y of s as 1 by s into 1 by s plus 2. Now by taking the inverse Laplace transform, we will get the answer as option A. Now coming to the next problem, that is, it is given that A equal to a matrix minus 5, minus 3, 2, 0, and we need to calculate the value of A cube. Now by the matrix property, that is capital A, we know it is a system matrix. So by means of the matrix algebra, we have determinant of SA minus A equal to represents the characteristic equation. Here it will get s square plus 5s plus 6. Then by replacing s by capital A, we have a square plus 5a plus 6i equal to 0. From that we can get the expression for a square. Then to get the a cube, we need to multiply that expression into capital A. Thereby it becomes a cube equal to minus 5a square minus 6a. Now by replacing a square by means of the expression minus 5a minus 6i, we will get the answer as B. Okay, now the next question is regarding this. We have the state equation and output equation is given, and we need to find the transfer function. So the first step is we need to express the given equations in matrix form. Thereby we will get it as like this, that is state equation and output equation will get like this. Then by applying the transfer function matrix equation, that is g of s equal to c sa minus a inverse b. Here capital D is 0, that is why it's reduced from c sa minus a inverse into b, and you will get the answer as capital option A. Now coming to the next problem, to find the state transition matrix of the system. So we know the state transition matrix of a system is given by phi of t equal to inverse Laplace transform of SA minus inverse. So by directly substituting, we will get the answer as C. Now coming to the next problem, we have a discrete time system is given with a state equation and initial conditions are there. Now we need to find the pole location of the system when A equal to 1, small a equal to 1. Now by replacing the matrix A, that is our system matrix A, by using the expression small a equal to 1, we will get the system matrix as A equal to 1, 0, 2, 1. Now for a discrete time system, the characteristic equation is given by determinant of zi minus a equal to 0. And by solving that, we will get it as z equal to 1, 1. So the poles locations are at 1, 1, and the answer is option A. Now going to some more problems. That is, consider the system described by the following state space equation. We have the state equation and output equation is there. If u is a unit step input, find the steady state error. Now steady state error, it is nothing but the deviation of output with respect to the input. So initially we need to find an expression for response y of t. Now you can use the any method. You can approach the transfer function approach, that is g of s equal to c sa minus inverse b plus d form. By substituting that, we will get the transfer function. Then that is y of s by u of s equal to g of s form. From that we are able to find y of s. By taking the inverse Laplace transform, we will get the y of t. Or in other words, another method is we have the given state space model is in controllable canonical form. So by observing, we can directly write the transfer function of the given system. Now after forming the transfer function and find the y of s equal to u of s into g of s, then find y of t. Now when t tends to infinity, we will get the value of y of t at the steady state value. Now u of t minus y of t at t tends to infinity, that is gives the steady state error. Here it becomes 0, that is option is A. Now the next question is, the state variable representation of a system is given. We need to find the response y of t. Here also we can adopt the same method as discussed in previous one. You can go for the transfer function approach. That is here we need to find the response y of t. Since the initial conditions are there, we need to find the solution of state equation, that is x of t equal to phi of t into x of 0, where phi of t is the state transition matrix. Thereby you will get the solution of state equation. Then by substituting in the output equation, we will get the required response y of t. Here the answer become D. Now the next question, that is regarding network is described by the state model. It is given. We need to find the transfer function. Again, from the given expressions, first we need to make the state model in matrix form. Then by using the formula g of s equal to c sa minus inverse b plus d, we are able to find the transfer function. We will get the answer as option A. Now the next one is, a system is represented in state space is given. The matrix A is 1, 2, alpha, 6 and matrix B is 1, 1. The value of alpha for which the system is not controllable. Now it is in connection with the controllability of the system. So first we need to form the controllability matrix, that is QC equal to BAB. Then by using that relation, that is we know the system should be controllable only if determinant of QC not equal to 0. Now you can form a relation for the alpha and you will get the answer as alpha equal to minus 3, that is answer is A. Now the next question, it is again in connection with the controllability. We have a state space model is given. Now by using the matrices capital A and capital B, we can form the controllability matrix initially. You will get you can form the controllability matrix, that is QC equal to B A B A square B. Now by the property, that is the system will be controllable if determinant of QC not equal to 0. Then by you will get a relationship of A1, A2 and A3, and it is the answer becomes option D, that is A1 should not be 0, A2 should not be 0. That will be the criteria you will get, such that the determinant QC not equal to 0. So the answer is option D. Now the last question, that is it is in connection with the controllability and stability. So we have a system state equation is there. Now we need to check two things. Controllability, it can be checked by using the controllability matrix QC, and it is you will get the matrix QC determinant of QC becomes 0. So the system is not controllable. Similarly, by using the matrix A, we can find the characteristic equation, that is determinant of SA minus A equal to 0. Here also you can see that this system having poles on RHS of S, that is eigenvalues having positive real part. So system is not stable. Hence the answer is B. So these are the some questions we discuss in state space analysis. Thank you for listening. Thanks.